Exponential functions are often used to model a lot of different things. One of those is population data. Um, Another might be financial data. We'll look at some of those, I think, in a bit. But here we've got where we're going to use an exponential function to solve a particular problem that's being described in front of us right here. And this is a population problem. This is modeling a population, actually, of bacteria. So it says a certain bacteria population doubles every 20 minutes. Ooh, think about that, doubling every 20 minutes. Beginning with 10 cells, 10 bacteria cells in a culture, the population can be represented by the function b equals 10 times 2 raised to the power of t. So we got 10 cells to begin with. That 2 is where we're doubling. We see this doubling factor here. And t is time, and we're doubling every 20 minutes. So B is the total number of bacteria cells. T is the time in 20-minute increments. And then it says, how many will there be after 2 hours? Well, first off, let's think about, we talked about how that an exponential function is A times B raised to the power of X. And in this case, we do actually have an A, and that's 10. That's kind of our beginning point. One way to look at this is that B is our final amount, or an amount over time with respect to time. In this case, after 2 hours, what will our total population of bacteria be after 2 hours? This is what we're trying to find out. And where B is where A is 10, that you might say is our starting point, our original amount. And our base is 2. That reflects the doubling. This population is doubling every 20 minutes. And T, I put X here instead of T. This is with respect to time, habit, and T. So I've actually got the function here. And really all I really need to think about is, in order to solve this algebraically, is what's T? What's T going to represent? Well, if we're doubling in 20-minute increments, I need to think about how many 20-minute increments are there in 2 hours. Well, there's 3 every hour. 3 times 20 is 60. That means that there's 6 20-minute increments after 2 hours. And so to solve for B, this is just going to equal 10 times 2 raised to the 6th power. Well, hopefully you would know by now, you should know, begin to know, that 2 to the 6th is 64, and 64 times 10 is 640. So after 2 hours, we've gone from 10 bacteria cells to 640. Wow, that's a pretty rapid growth, but that's characteristic of an exponential function. It zooms out of sight. It has, wait for it, exponential growth. I am going to graph this on the calculator because, again, I want to just make sure, I want to just show something here that is important, can be important as you're graphing this, and then we'll look at a table that will confirm our results. Well, let's just quickly graph our function. We were given a function B equals 10 times 2 raised to the power of t, or x. We're going to use x in this case. We're trying to find the total number of bacteria cells, where we started with 10. That's where the 10 is. That's the A, and the A times B raised to the power of x. And 2 represents the doubling. That is our rate, if you will. That's our rate of growth. This is an exponential growth function, where our t is the amount of time. And of course, we're in 20-minute increments, so we're talking about over 2 hours. But so let's see. We got 10 times, and I'm going to put the 2 in parentheses. 2, that's my rate of growth. And we're going to raise that to the power of x. We're going to use x here. And let's go quickly look at our graph. And boom, you can see that it really changed. One other thing about that 10, if you notice, look where my y-intercept is. My y-intercept, which in the parent function would be here when x is 0, y is 1. Now when x is 0, y is 10. That 10 has stretched this exponential function vertically, and it has changed that y-intercept to 0, 10. Let's go look at the table. And I can see that when x is 0, y is 10. And let's go down here and look, okay, what about when x is at 6? That's our exponent, 2 to the 6th power. And we can see that it does confirm our answer that we solved algebraically, that after 6 20-minute increments, starting with 10 bacteria cells, and the function that we were given, the fact that it was doubling every 20 seconds, in 2 hours, we would have 640 of these bacteria cells. A lot of rapid growth there, exponential growth. We can also have exponential decay. I think we're going to look at that here coming up shortly.